Here's a second example of finding the velocity, speed, and position functions given the acceleration function and some initial conditions concerning the velocity and the position. So remember, all right, that the velocity function is an antiderivative of the acceleration function, and that's going to be, in this case, the acceleration is 5 sine of t, so it will be 5, the antiderivative of 5 sine of t with respect to t. And when I antidifferentiate 5 sine, well, the derivative of the function who has sine as its derivative is negative cosine, so I get negative cosine, negative 5, I should say, cosine of t plus some constant, and I'll call it C1 again. I'll need another value of C in just a minute. And then remember V of pi over 2 is equal to 3. So evaluating our velocity function here at pi over 2, I'll get negative 5 cosine. Remember, every instance of t will have to be replaced with pi over 2. So I'll get negative 5 cosine of pi over 2 times c1. And cosine of pi over 2 is 0. Cosine of pi over 2 is 0. So this is going to be 3 is equal to c1. So then the velocity function is going to be negative 5 cosine of t plus c1, which we found to be 3. So there's our velocity function. And there we have it, okay? Our speed, well, speed is the absolute value of velocity. So that's going to be the absolute value of negative 5 cosine of t plus 3. I believe I better go back and look up just to make sure I have that. Negative 5 cosine of t plus 3. And that's it. This is our speed function. And then finally, our acceleration, our position function. All right, our position function is the position function is an antiderivative of velocity. So that's going to be an antiderivative of negative 5 cosine of t plus 3. And so let's see, who has negative 5 cosine as its derivative? Well, that would be negative 5 sine. Plus, who has 3 as its derivative? That would be 3t. Then plus a constant of integration c2. And now to figure out what c2, let's look at the position function at pi over 2. We're given that the position function at pi over 2 is 4, but the position function at pi over 2 is also equal to the position function where every instance of t has been replaced by pi over 2. So that would be negative 5 sine of pi over 2. Plus 3 times pi over 2 plus c2. And so let's see, sine of pi over 2 is 1. So this is going to be 4, forgetting about the middleman here, 4 is equal to negative 5 times 1 plus 3 pi over 2, all right, plus c2. So C2 is going to be equal to 4, right, plus 5 minus 3 pi over 2. All right, so filling this in, we'll have that the position function at time t is going to be negative 5 sine of t plus 3t plus c2, which is going to be 9, 5 and 4, minus 3 pi over 2. And that should be our position function. Let's check. I think I have it here, and that's correct. Let's take a look at another example. All right, let's remember that in this case we're going to calculate displacement and distance. All right, using from this, and remember displacement was a change in position, so it would be s1, s of t, the final value of the time minus the initial value of the time. But if you think about this, that's just a definite integral of velocity from the initial time to the final time. So let's suppose that our velocity, all right, is 2t minus 4 feet per second. The displacement, which is equal to the change in position, is going to be the definite integral of velocity on the interval from 1 to 5. Now think about why this is true. We'll talk about this as this progresses. First thing, we'd have to calculate an antiderivative, so we'll have 2t squared over 2, which is just t squared minus 4t. And if I would add on, I'll just temporarily add it on a constant integration. This would be the position function for some t, for some c. All right, but I'll evaluate that from 1 to 5. So I'll have the position function at 5 minus the position function at 1. In each case, this constant won't change, so I'll really be subtracting it off, so I'm just going to get rid of it now. We won't have to worry about it. We just have to integrate the velocity, all right, to get the displacement. And so at 5, this is going to be 5 squared, 25, minus 5 times minus 4 times 5, 20. Okay, minus the value at 1, which would be 1 squared, which is equal to 1, minus 4 times 1, 4. So this will be 5, okay, minus a negative 3, and that will be 8. Our displacement is 8. So the object ends up 8 places further in the positive direction at 5 than it started with at t is equal to 1. Okay, so the displacement is 5. Now notice here we have here's the velocity function. This is v of t, and I just integrated from 1 to 5 to get the displacement function. To get the displacement, I should say, the displacement over that interval. All right, now let's find the distance traveled. To find the distance traveled, well, we have to take into consideration that this thing is going to be backing up sometimes when the velocity is negative, but it will still be traveling, all right, and it'll be going forward when the velocity is positive, but again, it'll still be traveling. So to get the distance traveled, I'll have to integrate, all right, in this case on the interval from 1 to 5, not velocity, but the velocity's average value. I integrate, basically, I'm integrating speed. And that will be the integral from 1 to 5 of the absolute value of 2t minus 4 dt. All right, and now let's think about this. I'm going to need to split this up. So start with, where is 2t minus 4 equal to 0? Well, that's going to be when t is equal to 2. So I'll split this at 2. All right, I have the integral from 1 to 2 of the absolute value of 2t minus 4 dt, plus the integral from 2 to 5, the absolute value of 2t minus 4 dt. Okay, now let's see, on this interval between 1 and 2, all right, I think that if we look at this, between 1 and 2, 2t minus 4 is going to be a negative number. So what we'll have to do is we'll have to integrate the absolute value of that. It's going to be negative 1 times 2t minus 4 dt, plus on this integral from 2 to 5, 2t is going to be bigger than 4, so this will be positive. So I'll integrate from 2 to 5, 2t minus 4 with respect to time. Okay, this is going to be, the first one's going to be the integral from 1 to 2 of 4 minus 2t multiplying by negative 1, plus the integral from 2 to 5 of 2t minus 4 dt. Okay, so let's see. So what's this? The antiderivative of 4 is 4t. Antiderivative of 2t is t squared. So I'll have 4t minus t squared from 1 to 2 plus t squared minus 4t, all right, from 2 to 5. Let's see, if I evaluate this first one, when I evaluate this at 2, I'm going to have 4 times 2 is 8, minus 2 squared is 4, and then evaluate it at 1, 4 times 1 is 4, minus t squared is minus 1, so I'll have that amount, okay? Plus, evaluating the second integral, I'll have t squared, but at the upper limit t is 5, so that'd be 25, minus 4t minus 4 times 5 minus 20. And then I'll have the value at 2, t squared, when t is equal to 2 is 4, minus 4t at 2 is 8. So let's see, so what do we have here? We'll have 4 minus 3 plus, here I'll have 5, all right, and then minus a negative 4 or plus 4 is 9. So this is going to be 1 plus 9 is equal to 10. So it'll have traveled, even though the change in position was only positive 8, the distance traveled was 10, meaning that it backtracked a little ways, so that there'd be a change in distance, but not a change in position. So here's the idea. Remember, we had that basically I have to take this and anti-differentiate the absolute value. Remember, the function before looked something like this. And when I reflect that, when I change the absolute value, I take the negative part of that, and it gets reflected across the y-axis. So this area that's shaded here represents the distance traveled. Okay, all right. I think that's the end. I'll have another video with a few more examples.